So I'm Samuel, and I've been working for nearly 4 years at Octo Technology as a data scientist, mainly in the industry field. So Octo is a consulting company based in Paris. So I saw that some people from the New York Times are part of the attendance, and I'm here to answer one of their questions here, how to build AI we can trust. So I'm joking. Of course, I don't have an answer to this one, but more seriously, I'm convinced that in order to trust our models, we first need to know how confident they are in their own predictions. So what do I mean by that? Well, let's start with a little game. So imagine that you have some money and you're a data scientist, which thankfully can happen at the same time. You want to invest that cash into some product, hoping for some return. So your first reflex here is to build a super tuned machine learning or deep learning model. And after a bunch of analysis, you're hesitating between two products, A and B, and your model gives you the price expectation, for example, over 1 year. So what product do you invest in here? Please raise your hand if you choose model A. Okay, and choose model B. Well, right, okay. B seems also the right option to me, since as we will make more profit over the year, according to this plot. Well, only if we consider the mean expectation. Indeed, if I include the uncertainty in my decision-making process, do you still make the same decision? Well, maybe not. Depends if you're a gambler. For a gambler, you might go for B, but personally, now I go for A. So my point here is exactly that. Making decisions based on data is hard, but if we were a bit more disciplined about quantifying the uncertainty, we might make better decisions, okay? So I started thinking about it when I saw this tweet from Eric Bernhardson. New Year's resolution: every plot I make during 2018 will contain uncertainty estimates. So I thought, this guy is definitely right, and I have to do this as well. And that's why I've been working on this topic, trying to find some pragmatic techniques that allows to get insight about uncertainty in machine learning models. So I'll try to share some insight with you today. And we'll start with a journey through random forest. And also for that, we will dive into an example, a pragmatic example, to illustrate the construction of prediction intervals. So I choose the critical temperature for superconductivity forecasting dataset. And according to Wikipedia, a material is said to be superconductor if it has a critical temperature below which the resistance dropped abruptly to 0. Okay? So the goal here is to predict for a given superconductor material the minimal temperature from which it becomes superconductive. So the target variable, Y, here is in Kelvin. So let's start with some quick reminder how to build a decision tree for regression. The idea is to recursively create splits by minimizing a loss function, for example, the mean square error. And a binary split is defined, like we can see, by a variable. Here it's NOx and a threshold 2. And the predicted value in each leaf is the mean of the sample that fall inside, okay? So to find the optimal split, we iterate over all features, we iterate over all splits, so that's a greedy algorithm. And the best split is the one that minimizes the mean square error in the left leaf plus the mean square error in the right leaf. So this is done until a leaf is pure. So a pure leaf means that there is only one observation or several that have the same target value. So we can't split it anymore, okay? So now you will build a forest with those trees. So a forest of trees is built by using the badging techniques. And badging stands for bootstrap aggregating. So we built a lot of decision trees, 1, 2, etc., and 1000, by bootstrapping. So it's basically you're making sampling with replacement on your data, and then you aggregate all those constructed weak learners by averaging the predictions. And it gives you an estimate, and if you take the mean square error, it's the conditional mean, okay? Okay, now one day I was reading one of my favorite blog here, Data Dive, and when I came over those three sentences. So one can use a random forest as quantile regression forest by expanding the tree fully. Then a prediction returns individual response variables from which the distribution can be built if the forest is large enough. And the nice thing is that those intervals can be cross-validated. Okay? So there are three main takeaways here. First, a forest large enough is an estimate of the conditional distribution. Second, prediction intervals can be cross-validated. And third, each tree has to be fully expanded. So let's do it. And this code here shows how to train a random forest with a well-known scikit-learn library. And we will build the prediction matrix on our superconductivity dataset. Okay? So the chosen criterion is by default the mean square error to estimate the conditional mean. Then we need, as we told before, we need many trees to estimate the predicted distribution. N jobs equal to -1 is just to parallelize the construction of the trees. And mil sample leaves equal to 1 is to indicate that we expand the trees until the leaves are pure. So there is a comprehension list here. So we iterate over each observation from the test set. Then we iterate over each trees from our forest. And we basically can make our prediction, okay? And that's how the result looks like. Here, for row 0, you have the prediction of your 1,000 trees, okay? So let's take a look at this matrix. For example, for prediction for the row 0, for this material, we see that every tree gives close prediction, okay? The model seems to be pretty confident here. So the mean predicted value is 2.5 and the max predicted value is like 5.4. Therefore, the variance seems higher on row 4 here. Predictions vary from 30 to 84 Kelvin. So the random forest doesn't seem to be so sure about itself on this sample, right? So a visualization of the density function will help us understand the repartition of those predicted temperatures. So I like this violin plot since, from the Seaborn library, since it gives us a good idea of the distribution. And here on the x-axis, it tells us which material we are looking at, 0, 1, 2, 3. And the y-axis is a range taken by the predicted critical temperature in Kelvin. The violins are the distribution. So this is quite different than a single point, as we can see. And we will try to interpret each conditional distribution here. So observation 0 and 1 seems to be a robust prediction since violins are wide. And the model is confident here. Okay? Observation 2 now is also robust, but it has some extreme value, as shown the tail in high temperatures. And the observation 3 is really uncertain. All trees have different prediction. Variance is very high. Okay? So if we just make a random forest here, we have 4 points. And with the technique I show you, we have all those distribution that gives us a lot more information, right? So let's take a step back now.
What does it mean that the distributions are multimodal?
Sorry?
What does it mean that they have multiple teeth?
I'm not sure. It means that there are two. No, I don't know. I don't know. Maybe some information about the underlying data. I don't know. So let's take a step back here and observe results for 100 materials. And as we'll not see anything with 100 of violin, we only plot the 90% prediction intervals. And those are built by taking percentile 5 and percentile 95 on those predictions, on those distributions, sorry. Here, okay? And the result looks now like this. Once again, axis, we find materials, so 100 materials sorted by increasing ground truth. And the y-axis is the temperature in Kelvin. So now try to remember point 2. It is possible to cross-validate the intervals. So this simply means that, here that we can count how many intervals contain the ground truth. For example, this one contains the ground truth, the sign point, and this one does not, okay? And the number, if we count over 100 intervals, there is 91 ground truth that are into those intervals. And guess what? This is right, since we have built 90% prediction intervals, so we are very lucky here. So now let's focus on another interesting thing. If you look carefully, predicted intervals for high critical temperature seems to be bigger than those for low temperatures. So the mean height of intervals is quite different, as you can see here. Why is that? It's a bit related to your question, maybe, because, I don't know, maybe some of you have any idea of why the model is more uncertain in high temperatures? Yeah?
The mechanisms are less well understood, and low temperature superconductors tend to be closer to pure elements.
Yeah, okay. That's the reason. So critical temperatures are in Kelvin, and they are mined by 0. So now if we look at the distribution of the target variable in the training data, we see that it's exponentially decreasing, again with a spike and the multimodal. I don't know why. I'm not an expert into that field. And yeah. So the model had way more data for low critical temperatures to learn. It's not surprising that it's more confident in this region, okay? In fact, the uncertainty in general is the sum of two different concepts. So it's either due to a lack of data in certain region or a limitation of the model. This is called epistemic uncertainty, and it is the one we can reduce. Like here in high temperature, we maybe need more data, or we need to have a better model or whatever. Or it can also be a real and irreducible variability, and this one is called aleatory uncertainty. For example, when you flip a coin, you can't predict what will be the result, right? So let's tackle point 3 now. We said before that each leaf must be pure, but what if we don't grow the trees fully? So this is a fully expanded tree. Each leaves are pure, and there are two cases. Here we have a leaf with a unique sample, and here, as I told you previously, there is a leaf with two samples that have the same critical temperature. So we can't split it anymore. So it was like 15.6, and the two samples have this critical temperature. Now in comparison, this is a pruned tree, and we have stopped making splits when the next leaves will have had less than 600 samples inside, okay? So parameter mean sample leaf is 600 now. Each prediction is now the mean of the training target value that felt inside the leaf, okay? So here it's a mean of the 618 target value. Hence, by having only means, the variance of our 1,000 predictions for all three has decreased. So it looks like this. When we look at the density plot for one sample, the distribution of predictions that look previously like the blue curve with a big variance is now with mean sample leaf equal to 600, the orange curve, and with a really diminished variance, okay? And by plotting the same figure as before, we observe that only 40 out of 100 intervals now contains the ground truth. So this is not 90% prediction intervals anymore. But there is something. So a solution is to keep all the training values in memory in each leaf. If we do this, we can actually reconstruct all the distribution from the training data set. So the scikit-garden package here implement this, and we can now build quantile regression forest with pruned trees. Okay? So we'll illustrate what happened in this package. Say we have a forest of two pruned trees, T1 and T2, with several predictions that failed inside with different target value. And if we do as before, the distribution would be composed only by two means here, y red and y blue. Okay? Instead of this, we keep in memory each training target value with their associated weights. And we use here, like this, and we use the weighted percentile method to find the prediction intervals. And this basically allows us to recover all the variance from the training data, okay? So I told you about scikit-garden package, and that's how we implement the prediction intervals. It's basically the same interface as scikit-learn, and then you make your 90% prediction intervals right again with mean sample leaf equal to 600. Okay? So, okay, so far we've seen how to get uncertainty by building prediction interval with random forest, but I guess not everybody here use random forest. So I was myself happy when I discovered this, but I asked myself, how can we generalize this to other machine learning algorithms, right? So one can use a custom loss function to fit the parameters, okay? Quantile loss allows us to fit a model that estimates the conditional alpha quantile. So we'll see how it works. Let's get an intuition here. This is an asymmetric loss. It will penalize more the data if you're above or if your prediction is above the ground truth or below. So imagine we are fitting a model. We try to find the parameters that minimize our loss function with a descent gradient or some optimization algorithm. So here, the example is with alpha equal to 0.1. So we should estimate the 10th percentile, right? We'll see that the absolute error is not penalized the same way if we are predicting a value above or below the ground truth. Let's take y1 equal to 7 Kelvin. And our prediction with random parameter, randomly initialized parameter, is equal to 12 Kelvin. So the error is -5. And on the graph, -5 gives us a penalty of 4.5. So it does come from here. Look at the formula. Our prediction is above the ground truth, okay? So we penalized the absolute error by 1 minus alpha, so 0.9, okay? So 0.9 multiplied by 5 is 4.5. Another example. Now our prediction is below. The error is +5. And it brings us to 0.5. And if we look at the formula, when we're below, when the prediction is below the ground truth, we multiply the absolute value by 0.1. So we have a penalty that is lower, okay? So this allows us to estimate quantile alpha, but just be aware that creating the 90% prediction intervals can be costly, since with this technique we need to train two models, right? One for the 5th percentile and one for the 95th percentile. So for example, if you're training neural network, you can wait forever to train both your two models. Here is some example of algorithms that implement directly this loss. So you have the gradient boosting regressor from scikit-learn. You've got also the Vopal Wabbit. It's an online learning algorithm. LightJBM, it's another boosting algorithm. Also XGBoost for the XGBoost user. And the last one is a quantile loss that we define in Python. For example, for Keras or TensorFlow or other framework that does not implement this quantile loss, we'll need to create our function and inject it as a callback. It's often doable. Okay? So here is the implementation, an example with LightJBM. So we define alpha equal to 0.95, and we will predict, we will make 3 models, one for the conditional mean, one for the 5th percentile, and one for the 95th percentile. Okay? Now we fit those models on our data, and we get those results again. We can cross-validate it and check that roughly 90 intervals contains ground truth. And this is another visualization of those intervals, because whenever you have 1,000 of points, you will not see anything with that. So we use this in practice, okay? Finally, I plotted for this part the prediction intervals sorted by increasing size, and also the difference between ground truth and prediction, as we can see in blue. And we observe that the bigger the intervals, the bigger the error is, okay? And if we compute the Pearson correlation coefficient, it gives us a 0.53. So it's quite a strong correlation, and it confirms us that whenever our model is uncertain, so the intervals are big, it is more likely to make bigger error, okay? So once again, this is great, but I can keep asking myself, like, we can continue and wonder what can be done if we're on a classification problem, right? So now it becomes a bit funny. Let me finish with an introduction to the calibration of probabilities, and we will first see 2 examples where good probability estimates are needed. So first one is in marketing. To evaluate which client brings more money, we usually compute the customer lifetime value. And it can be done by multiplying the price of a product, say a $200 umbrella, by the probability that the client will buy it, say 0.1. So we have a CLV of $20 here. So we need this probability. It's because they give a free umbrella that you love here. Okay. We need a good estimate, like a probability that have a physical meaning here. And in medicine, there are really sensitive results. So the probability of having a disease, for example, and also a probability with physical meaning is mandatory. So in frequentist terms, we want our likelihood to be the same as the chance of belonging to a class. What does it mean? For example, in binary classification, so 0 or 1, if we take our samples that are predicted between 0.39 and 0.41 here, so Y2, Y5, etc., we want the proportion of those samples to belong to class 1 to be near 0.4 here. With a binary classification, we can just take the mean of all these observations. So it means, if we're in this case, that there is really a 40% chance that they belong to class 1, okay? So the probability 0.39 or 0.41 really has a physical meaning here. In real life, I told you that because in real life, the method called predict-proba that we all use not every day, but almost, often returns bad probabilities due to the abstraction of this method. So it carries a name that don't reflect the real behavior of it, like we will see after. And this leads to calibration issues. So first, there is a way to visualize the calibration called the calibration curve. It is basically like this one, and scikit-learn implements it also. So You split the axis 0, 1, the x-axis in several bins. You select the observation that have predicted probability inside those bins. You compute the proportion of observation that really belong to class 1 in each bin. And if the classifier is calibrated, the proportion must be equal to the predicted probabilities. So it should follow a straight line like the red one here. Okay? So let's do it once again. Here, the calibration curve visualization is implemented in scikit-learn, and it outputs this. And in this example, we look at the probabilities of a logistic regression. So it has been fitted on simulated data, and by assumption, a logistic regression outputs real probabilities. So as we can see, this classifier is well calibrated. Okay? And below, you can find the histogram that shows the distribution of those probabilities. On the same data, the naive Bayes outputs really bad calibrated probabilities. And maybe some of you have an idea why. This is due to the fact that I'm sneaky and I simulated data with 3 redundant features. So it completely breaks the assumption of independence needed for this classifier, right? So all predictions in the histogram below here are very close to 0 and 1, okay? So for a prediction near 0.9, there is only a 60% chance to belong to class 1, and this is the symptom of an overconfident model here, okay? Now another example, so the contrary, support vector machine. It also outputs uncalibrated probabilities. It actually outputs a normalized distance to the decision boundary. I told you the predict proba method is just an abstraction. It doesn't always output probabilities, right? So this has nothing to do with real probability. And all prediction in the histogram below are close to 0.5. And for prediction close to 0.6, there is almost 100% chance to belong to class 1. Sorry. So this is a symptom of an underconfident model here. Okay? So there are several solutions to calibrate the probabilities, and one of them is known as isotonic regression. I will not go into detail for this one since I run out of time, but it's basically a minimization of the least square with a monotonicity constraint, okay? So as one other guy tell, I let this as an exercise for you to know why it works. So you take the bad probabilities as X variable and the associated ground truth as the target, and you fit the isotonic regression, and it gives you the right calibrator, okay? So now by composing the isotonic regression with the classifier, the bad calibrated classifier, we find well-calibrated probabilities. The orange curve here is composition of naive Bayes and the isotonic regression. So this is possible for every bad calibrated classifier, and just know that you need lots of labeled data since you have to fit 2 models here on different sets of observations, okay? Okay, so I'll conclude with 2 takeaways. If you train a regressor, compute prediction intervals. If you train a classifier, check if your probabilities are calibrated or not, and calibrate your probability if it's not the case. And just remember, uncertainty is not everything, and at the end you still have to make a decision. Thank you for your attention. So yeah, if you have some questions, yeah.
So, reach that you did with isotonic.
Yeah.
Well, don't you have a regularization problem there? Because you're going to end up having few samples of some of the marketing.
I honestly don't know, because
What would be probabilities of outcomes that are basically and then I assume you think by the frames of domain. And then
Yeah, I'm actually I don't know. I'd be happy to discuss that with you after, but I've got to think. Sorry? Maybe. I'm not sure. But- yes.
I'm just wondering in the kind of histograms of the predicted values, especially the ones that are whether the model has a good fit. You know, can you explain why I guess
This one here.
yeah, the histograms are very like this, why the more predicted values kind of on the 0 and the 1. I would have expected the kind of predictions to be uniform, I guess.
So here it really depends on how well is your classifier. So how well it can predict the probabilities. So for example, if you have data that have a lot of signals, all your probabilities will be near 0 and 1 because your classifier will be able to find the right answer. And if I add simulated data that are really tough to find correlation with the target, it would have more it would have been more near 0.5. It's linked with the the aleatory uncertainty here. How much you make signal into how much signal do you have in your data? Yes.
I tried to use Force CI for prediction intervals before. It's the package that based on like a Trevor Hasty based paper. That didn't give me much success. So have you had any success with prediction intervals behind these comments?
I don't know this package, but did you try to cross-validate the intervals, or like what do you mean by you didn't have any much in much
I had
text?
data that I reserved and I knew what the prediction interval should have been.
Okay.
But then when I implemented the package and compared it, the results were not very good.
Okay, so I can only advise you to try to make some regression with quantile loss or and compare it. So thank you for having me here.